I said yesterday that when we have the conditions for rolling, that is saying something specific to you as problem solver that you can count on this relationship being true for your thing that's rolling. Now, I want to be really clear. If it's not rolling and it's slipping, then you can't count on this. That's important because the very first thing I'm going to want to do after we get pretty comfortable dealing with rolling is I want to flip the script and then have a problem where the object transitions from sliding to rolling. That's a tough question and allows us to really explore this. So I want you to understand how rolling works. I know it sounds kind of ridiculous, like, well, it just things roll. Yes. But, I don't want to bring this up as something massive. I want you to understand that I know we studied some minutiae sometimes, but I want you to have a good, firm grasp of this. I want you to build the next cool ride so I can ride it. It's that simple. Now, the energy portion of this is easy. I don't want to mince words about it. The energy portion is easy. If I ask you to figure out how fast the object is traveling when it rolls to the bottom of the ramp, all you need to know is how much energy it had here. And when it gets to the bottom, it's going to have two kinds of energy at the bottom. I don't generally like to make a big deal about this and do 1,000 examples. So take note. I don't want to do that. All of you who want me to do it again when I double the mass or change the shape. All right? If it's rolling, I can count on this right away. What does that mean, Mr. Shelton? What are you talking about? Well, if it rolls from here, let's say I started a distance h above the ground, and I ask how fast is it traveling when it makes it to the bottom of the ramp? Well, just like the block sliding down the ramp without friction, the amount of potential energy the ball has at the top, which does not depend upon its shape, is going to be equal to the total amount of energy it has at the bottom. But that energy now gets divided. Some of that energy is going to be translational. Some of that energy is going to be rotational, which is why it's going to be going slower. Things that are harder to turn, we saw it. Things that are harder to turn take longer to get to the bottom. They don't have less energy. They just divided the energy up differently. So what does that mean down here? Well, it means that I'm going to have 1/2 I omega squared plus 1/2 mv squared at the bottom. So I'll tell you, let's say it's a round thing. Pick one of our 4 round things. Let's go with a disk. Okay, that's 1/2 mr squared omega squared plus 1/2 mv squared.
Good afternoon.
Now I'm going to continue this problem because I really feel like it. Play ball! All right. Seniors.
Ladies and gentlemen, seniors may be released today without their senior shirts. We will all dress up.
Because it's rolling, you get to make this substitution. And you should notice that when you make that substitution, and be careful, we can make this substitution, but you need to be careful about making the substitution to understand what R is. Okay, be aware, R can be a fickle thing. And if you don't understand what I mean, consider the possibility that you could have something that has a different R than how big or how small it is. So we'll see some examples of that, but we can manipulate R a little bit. You need to check, make sure that one rotation of the object still corresponds to the center of mass moving one circumference. And in this case, it would. It's pretty obvious. But you'll notice that gets rid of the R's, right? And clearly shows you how now the energy is being divided. Is it pretty clear? So our object's going to be traveling slower when it makes it down there than it would if it could slide without friction. But the rolling object helps you deal with the fact that there's friction. Right? We always have friction, so it's always always probably easier to roll something down a ramp than it is to try and push something down a ramp that has to slide against friction. Now, that part's not particularly interesting. Adding this to the problem isn't going to really change the problem much, but you should be aware. That's what we're talking about when we say you can now figure out how fast something's going at the bottom if it's rolling down there. But they have to say rolling so you can use this substitution. So in any problem where they ask for velocity at the bottom or even perhaps the acceleration of the system, I would probably use energy, because anything else is going to involve the use of force. But let's be clear. The moment we have to do this problem using force, the problem changes dramatically. And we don't have time to explore it today. I guess I wasted too much time or did too much homework. But there are just 3 forces that act on the system: the weight of the system, the normal force on the system, and what direction do you think the frictional force is acting on the system? Up or down? It would be acting up the ramp. Because we're assuming, and I'm being careful, we're assuming that the object's going to roll down the ramp. We're not assuming the object is rolling up the ramp. We're assuming it's rolling down the ramp. That will affect the direction of friction. Here's what most people don't think. They don't think that the net force is happening now because it's rolling. But this problem still has mg sine theta acting down the ramp and still has friction acting up the ramp. You still have to apply Newton's second law to this problem. In the same way that the normal force is going to equal mg cosine theta. That is still the same even though the system is rolling. The forces don't change. However, this is probably never going to be an equal sign. It takes much less friction to roll than you probably have available. Meaning you'll probably never use this. Finding friction in these problems is actually kind of hard. So what we left out is how to deal with net torque, and that's going to have to wait till Monday.